Some say love.
This is an overview of mission security. So let's say that you need to protect some valuables and you've designed a tripwire system that's based on light. So we've got a laser. The laser is going to shine a red light across a hallway in your home. It's got to be pretty dark. And that red light is going to be hanging out, illuminating a sensor until the bad guy comes. So this is a graph of what's going on at the sensor. The light is on, it's on, it's on, it's on, it's on, and then the burglar trips the wire and blocks the laser just ever so temporarily, okay? The beam gets blocked, and that is going to set off a sound at the sensor box. A little siren's going to go off. That siren's going to blare for some amount of time that you're going to set, and then the system will be back armed again. Okay? So that's the overview of the behavior of the system.
And it can't be so.
The 555 timer in monostable mode. Monostable just means that there's one output, and then there's a trigger, and then there's another output temporarily, and then it goes back to its stable mode. So what I'm going to do is step you through the wiring here. It's very similar, and the behavior within the internals of the chip is going to sound very familiar, but there are some key differences. So basically, when the I want to introduce you to what's being wired up here in my example. We've got this switch here. It says PBMO. It's a push button momentary on. And when this button gets pushed, that's going to be our trigger signal. Okay, we're at the end of this little lecture, we're going to replace that trigger signal with the blocking of a light going to a sensor. But just for simplicity now, let's say that when you push that button, that starts the cascade of events. Okay, now before the trigger pulse is applied, the overall output of the chip is low. And what I mean by that is that the discharge transistor is on, and the pin 7 short to ground is keeping the capacitor discharged because, as you know, this output inverter, if the output is low, the output of Q bar is high. And when Q bar is high, the discharge transistor is on, and the capacitor doesn't have the ability to build up any charge. Okay, now usually, so before the trigger pulse is sent, okay, the voltage at pin 2 is high. And what that means is that the input to comparator 2 is far above 1/3 VCC. Okay, and then that's why the flop is in the state that it is with the Q bar output high. So a negative going trigger pulse, okay, that's going to be the push button momentary on. It's a negative going trigger pulse. Okay, it's going to send the voltage at pin 2 basically to ground. So this voltage is going to go to ground or very, very low. And that is going to, when it's applied to pin 2, force the output of comparator 2 high. And then that's going to set the output Q bar to low, okay, which is going to change the output of the circuit to high. And it's also going to turn off the discharge transistor, which means that this circuit here that was allowing the capacitor to discharge is now cut off, so this pathway no longer exists, and capacitor C starts to charge. Okay? So the moment that the trigger, so just a quick review, the moment that the trigger signal is sent, the discharge transistor turns off, and then the capacitor starts to charge. So the capacitor is charging, and you'll see here that the capacitor is reading out at the voltage at the top plate of the capacitor is reading out at the positive terminal of comparator 1. And remember, comparator 1 is the one that's comparing to 2/3 VCC, right? That's the first stop after the 555 resistor series thing. So once the voltage at the capacitor plates exceeds 2/3 VCC, the flip-flop gets reset, and then this output at Q bar goes to high, okay? And then what that does is it turns on the discharge transistor, and then it allows the capacitor to discharge again, okay? And then in that situation, the output here goes low, and it will stay in that stable state until the trigger is applied again. So let's have a look at what this might look like in terms of timing diagrams. So as you know, these timing diagrams are pretty helpful, I think. So we've got the voltage at the input. So this is the voltage that's being read to pin 2. We've got the voltage at the capacitor, the top plate of the capacitor, and that's being read to pin 6. And then finally, we've got the voltage at the output, that's pin 3. So initially, like we were saying before, the input voltage is being held high. Okay, and by the way, it's being held high by this thing called a pull-up resistor. You don't really need to worry about that, but basically the idea here is that the voltage is VCC when the circuit is in its stable state at pin 2. So we start off at VCC, right, and then all of a sudden, this little push-button momentary on trigger pulse is sent. Remember, that's going to be the blocking of the laser eventually. And then the voltage gets sent to ground just temporarily, pretty briefly. Okay. And what ends up happening here is, like we were saying, the voltage at the capacitor, which is staying discharged, right? The moment that trigger happens, the discharging circuit goes away, and then the capacitor starts to charge up, okay? And you'll notice, by the way, that it's charging up through R1. So it's charging, and then all of a sudden it hits 2/3 VCC, which is going to then reset the flip-flop, and then we're going to see that the capacitor then has now a discharge pathway, okay? So what we end up seeing at the output is we see that the output is initially low, or almost zero, and then all of a sudden the output jumps up to high, which remember is VCC minus about 1.5 volts, and it's going to stay high until the capacitor discharge circuit returns. Okay? So this discharge has a value of 1.1 R1C1. That's the amount of time that the capacitor takes to charge up to 2/3 VCC. You don't have to worry about where that comes from, but what that's going to tell us is the width of our output high pulse, which actually is going to be the amount of time that your siren stays on. So for example, if you want your siren to stay on for 10 seconds, that formula is going to be how you calculate that. Okay? Hi, Double E. This last piece is going to be about figuring out how we're going to send a light-sensitive, negative-going, brief trigger pulse to pin 2. Now, we're going to use a voltage divider, so let me just remind you what a voltage divider is. A voltage divider is a circuit where you take a series connection of resistors and you drop voltages between the power supply and ground. So let's say that our VCC here is 9 volts, and I've got two identical resistors, R and R. That's going to put this voltage here at 4.5, okay? And the reason why that's going to be 4.5 is because we know that the voltage has to drop identically across these two resistors because the current through them is the same, okay? And Ohm's law tells us that the voltage therefore has to be the same, so that the two identical resistors are going to split the voltage equally. Okay, well then what happens if the two values of these resistors are not the same? Well, let's say that this voltage that this resistor here is tiny, like we'll call that lowercase r. Maybe instead of being equal to r, let's say that it's maybe 1/100th of r. Well, if these two resistors have the same current through them, which they do, okay, because the way they're connected is in series. There's no branches for the current. You forget the pin 2 for a moment. There's no branches. If they have the same current, the voltage across the small one is going to be small, and the voltage across the big one is going to be big. Okay, think about it this way: voltage is the push. If the resistance is tiny, you need less push to get the same current. If the resistance is big, you need more push to get the same current. Okay? So if, let's say the tiny resistor is 1/100th of R, you're going to get 1/100th of the voltage difference across the big R. Okay? So what two numbers add up to 9 volts here to give me, to satisfy that? I don't know. It's going to be something like the voltage drop across the top one is probably going to be really small, like maybe 1/10 of a volt, okay? And then the voltage across the top one, the bottom one, which is the larger resistor, is going to be almost 9 volts, okay? So the voltage divider here is really key, and I just want to encourage you to think this through carefully. The point is, though, that if you have a tiny resistor here and a big resistor here, the voltage at pin 2 is going to be very high or close to VCC, which means that the behavior of the circuit is going to be what we wanted or thought. Okay, so then the question is, how do we get our negative going trigger pulse? Well, if you're following the voltage divider argument, it would be really nice if we had something that could make this resistance big. Why? If we made that resistance big, this voltage drop would have to get smaller, right? Because it would have to accommodate the increase in voltage drop across that guy, because they always have to add up to 9 volts. It's a little bit like if this resistance gets bigger, you're pushing that voltage down. So then let me introduce you to the way that we're going to push the voltage at pin 2 down by making the resistance in that top branch bigger. Okay, we have a new device in EE in this unit called the photocell. Okay, the photocell, it's got this kind of like tiny glass cap with a squiggle that looks like that in it, and it's got these two long legs. And the photocell is kind of cool because when light is shining on the photocell, this thing conducts electricity really well. You guessed it. There is an NP junction inside there. We're gonna not talk about that right now. But when the light is shining on this, the resistance is really quite low. When the light turns off, the resistance gets quite high. So that is going to be how we send our negative going trigger pulse. We're going to make sure that we have a light-sensitive resistor. The symbol for that is resistor in there with a little light coming into it. And then here, we're going to put a second resistor, call that R3, and then this guy's going to be called R2. And the idea would be that when this light is on, okay, the photoresistor has a very small resistance, so most of the current's going to go through here, okay, and that's going to be our situation where most of the voltage drop, if not almost all of it, is across this one. So very little drop here, and then when the light goes off, okay, we end up having a much higher, when the light goes off, we have a much higher total resistance here, which drives this value low. And then when the light turns back on, this value goes back to high. So that's going to give us our trigger pulse, right? Because what we said was that when the laser gets blocked, we want the signal to go low and then return to high when the laser comes back on. Okay, so that's how we're going to end up triggering pin 2 and setting off the set of events where the siren goes.
I'm a millionaire. I'm a millionaire.